All right, we're going to start out with Theorem 21, and Theorem 21 says the following: that every finite integral domain turns out to be a field. Remember, previously we proved that every field consisting of more elements than just zero, every field is an integral domain, but example 17 should be an example of an integral domain that's not a field. But this theorem 21 tells us that if my integral domain is finite, that is, has only finitely many elements in there, then in that case it is a field. Okay, so let's see how the argument goes. Suppose R plus dot is a finite integral domain, and we're going to pick a non-zero. Now, remember, the definition of a field is any non-zero element has a multiplicative inverse. So we need to show A is a unit, right? A unit means it's got a multiplicative inverse, right? Inverse under dot. All right, so what I'm going to do is I'm going to define a function going from R to R. And what does my function do? It multiplies by this A. Okay, so phi of R is just A dot R. Now I'm going to claim phi is injective. All right, so how do I prove that? Well, I suppose phi of R1 is the same as phi of R2. But what's phi of R? It's A times R. So I get what? AR1 is the same as AR2. But remember, Theorem 15 says that I have cancellation whenever I have an integral domain. Therefore, R1 has to equal R2, and I have just shown that phi is injective. Now, if I just look at phi going from R to its image, right? So there's the image of phi. Now, any map going from a set to its image is automatically surjective. Well, so I've just shown it's injective. If I only look at the image over here, then that map has to be surjective as well. Therefore, it is bijective. Remember that if I have a bijective map from one set to another, that's exactly what it means for them to have the same cardinality. All right, so what do I conclude? The cardinality of R is the same as the cardinality of phi of R. Okay, and both of those cardinalities is less than infinity because I have a finite integral domain. But now think, phi of R is a subset of R. So here I've got this subset of R that has the same number of elements in there. What does that tell me? They have to be the same set. So phi of R is exactly all of R. Now, what is in R? Well, since R is an integral domain, I know R has 1 in it. But if phi of R is R, then that says there's something in R, we're going to call it B, such that what? Phi of B is the element 1. But what does that mean? That means phi of B is A times B, because that's what my map phi does. So I get A times B is 1. Now remember that an integral domain is commutative. That's one of the properties. So not only do I know that A times B is 1, but I know A times B is the same as B times A, and they're both 1. Well, guess what? That tells me that B is the multiplicative inverse of A. In other words, A has a multiplicative inverse. And what does that imply? That A is a unit. That's exactly what it means to be a unit. So what did I do? I assumed I had A non-zero, and what did I show? It had to be a unit. Therefore, my theorem is proven, and I've shown that every finite integral domain is automatically a field. All right. So let's go through some definitions that I'm going to claim are common sense. Depends on how common your sense is. A subring S of a ring R, what does that mean? Well, it's any subset that's also a ring, right? That's what subring should mean. Definition 23, an ideal I of R is a subring of R, so that's the first thing it's got to be, subring. And it's got this strong multiplication property to it that says what? For any I in R, for any I in big I, in my ideal, and for any R in R, R dot I has to be the same, has to be in I, and I dot R has to be in I. Now, for if I is a subring, all I'm guaranteed is that if I take two things from there and multiply them, I get something back in my subring. But an ideal is even stronger than that. An ideal is if I pick anything in my ideal and I pick anything in the ring, bigger set, then I still have this containment property that R dot anything in the ideal is back in the ideal, and the ideal dot any R is back in the ideal. So an ideal is a subring with this stronger multiplication property. All right. There are a few exercises here that at some point I'm going to assign for homework. I might talk about exercise 26. Remember, Zn under addition and multiplication is a ring. So here I'm looking at Z12. Now it's a ring, but here I'm asking you to solve these linear equations. Well, arithmetic works the same under Z12, aside from the fact that some elements, namely 3 in Z12, do not have multiplicative inverses. And if they do not have multiplicative inverses, then you just can't cancel or divide by 3. So at some point, you're going to have to divide by the equivalence class of 3. You can't just do a division. So what you're going to have to do is ask yourself what values of x satisfy 3 times x equal to, well, whatever you get over here once you take this over to the other side. All right, so there's a hint on exercise 26. Now let's go to theorem 27. Theorem 27 says, suppose R plus dot's a ring and I is an ideal. Then I'm going to claim that if I contains a unit, then I has to be the entire ring. Now that's an interesting result, and it actually comes from that stronger multiplication property that I talked about. All right, so let's see how this argument goes. We're going to need to show, see, since I is an ideal, well, I is a subset of R, but I'm going to claim I is equal to R. It's the same ring. All right, so since I already know I is a subset of R, I just have to show R is a subset of I. Remember, that's the way we showed two sets are the same. Okay, so how do I do that? And the answer is I pick something in R and I have to show it's an I. All right, so that's what I do. I choose something in R. Now, it's assumed that I contains a unit. Okay, so if I contains a unit, there exists A in I that is a unit. What does it mean to be a unit? It means I have an A inverse. Now, where does that A inverse exist? I don't know, but I know it's in R. All right, so now I'm going to write R in this clever way. R is the identity in the ring times R. But now I can write the identity of the ring as what? A inverse. So R is A times A inverse R. Now what's so special about that? We'll go back to definition 23. Definition 23 says that if I have anything in my ideal multiplied by anything in R, I'm back in my ideal. Well, look at this up here. A is in my ideal. A inverse R is in R. So I've got something from my ideal multiplied by something in R, and definition 23 tells me, since it's an ideal, then that thing, this whole thing, has to be in I. Well, what is that whole thing? It's just R. Therefore, R is in I. So what I do, I pick something in R, and I showed it had to be in I. Therefore, R is a subset of I, and I am done. Okay, let's try to get one more theorem out. Theorem 28 that says what? If I have a ring epimorphism, remember that's a surjective ring homomorphism, and if R is an abelian ring, then R hat is an abelian ring. You should notice that this is going to be an argument similar to one we've seen before. All right, so remember, R and R hat are automatically commutative with respect to plus. I just need to show they're commutative with respect to dot. All right. So I pick two things in R hat over here. Since phi is an epimorphism, there is an R1 and R2 such that phi of R1 is R hat 1 and phi of R2 is R hat 2. Then R hat 1 times R hat 2 is phi of R1 times phi of R2. Phi is a homomorphism, so that's phi of R1 times R2, which is phi of R2 times R1, which is phi of R2 times phi of R1, which is back to R hat 2 times R hat 1. And so I've shown that dot is commutative, and that's all I need to show. Well, that finishes theorem 28, and I'm going to stop here.